Okay, sorry for this technical hiccup. But as I was going to say, it's a pleasure to be here telling you about this work I did with my postdocs, Anne and Che, my PhD student Roger, and Xin-Ping Yang from Beijing, as well as some previous work I did with my group. Let me start with an introduction to the functions and numbers in quantum field theory, and then talk more about these particular elliptic numbers and functions we encounter before really going to the bulk of this project. So the motivation is to understand what numbers and functions occur in quantum field theory. Why? Because these are relevant for all kinds of checks of nature, ranging from the LHC to this G-2 mu experiment to gravitational waves, where we do encounter complicated functions if we go to sufficiently high orders in perturbation theory. Now, we don't only want to know what functions they are, we also want to be able to manipulate them, so we need their identities and fancy tools, ideally, to expand our calculational reach. Just starting at one loop order, what we encounter, for example, in this bubble diagram here in 2 dimensions, is a logarithm of the mass and s, which is now the momentum squared going through this loop. And if we go, say, to this box in 4 dimensions, we also encounter logarithms. These, in general, polylogarithms are defined as iterated integrals, where we're iteratively integrating dt by t with the polylog of 1 lower weight. And this is starting just with the usual logarithm, or rather minus the logarithm of 1 minus x. More generally, what we find in the simplest quantities in quantum field theory and always at one loop is so-called Goncharov polylogarithms. So here the integration kernel was only dt by t. Here it was dt by 1 minus t. And now we are also allowing for something slightly more general, dt by t minus ai. Now, these functions are fortunately very well understood, and one of the main tools that makes them very well understood is the so-called symbol. So it's defined via the total derivative. In particular, if the total derivative of such a function can be written as a sum over now easier functions times d log of phi I, this being some kind of form more generally, then we can iteratively define the symbol as now replacing the d log in a tensor product with a logarithm, and then on the other entry of the tensor product, we have the symbol of the simpler function. So here we have tensor products, which are multilinear and easy to manipulate. And moreover, the entries in these tensor products, logarithms, are very well understood functions, because we know in particular the identities they satisfy, stuff like log AB equals log A plus log B. And that makes polylogarithms via the symbol very easy to manipulate and well understood. So in a cartoon version, the idea is to decompose these complicated functions into simpler building blocks, just as we would do with Lego bricks. And since I was told most of you aren't working with the symbol, I'm going through a quick example here. So for the dilogarithm, we know that it is defined now as iterated integral with a d log of t, and then d log of 1 minus t with this minus sign here. And this means from this definition here of the symbol is just minus the logarithm of 1 minus x tensor log x. And one advantage is now that we can use this to derive identities also for the dilogarithms. Here, to make it fit a slide, I've selected what's maybe the simplest identity. So we can start with the dilogarithm of 1 over x and compute its symbol. And this is just inserting 1 over x into this formula. But now we know that the log of 1 divided by x is minus the log of x. And we can write this here as x minus 1 divided by x and use the rule here to find this expression for the symbol. And then we realize that this is nothing but the symbol of minus the dilogarithm minus a half times the logarithm squared. So this now indeed gives us a candidate for some identity. And it's indeed the case that this is part of an identity. I say part here because the symbol is agnostic to these factors of pi, but there's a more general framework called coproduct in which we can systematically reinstate them. So that's one very simple example how we can use the symbol to derive identities, complicated functional identities between these dilogarithms, but more general polylogarithms. Are there any questions so far concerning this example?
Yeah, I have a question. I didn't understand very well what is this tensor product. Because in the example, looks to me it's just a product.
I mean, it's a tensor product because there's an order. So we say this is the first entry and this is the last entry. And it actually matters whether something is in the first entry or the last entry, because the last entry is something that comes directly from the derivative. And the first entry is telling us something, for example, about the discontinuities of the functions we have. Does that clarify it?
But then it's just the product, the standard product, or you are doing the product between two different spaces?
When it's a tensor product, because I have this tensor, this being something different from that tensor, the first one.
It's not commutative.
It's just a regular product.
No, it's
So it's log times log, the number times the number.
Yeah, I mean, here it's with the log, this is totally symmetric. But here I have an order.
yes, and yeah, he's defining a new operation, right? It's center dot, or yeah, oh yeah. You're defining a new operation, so, and it's not true that they are commutative, basically. And from the definition is in the first line of the slide.
But then once you write log of 1 minus x times log of x.
No, but it's not times, it's this special times.
That log times that, what is that log times that?
It's just it's just the definition of
I didn't understand. Let's continue.
Yeah, I mean, it's multilinear, but it's multilinear in complex numbers, so I can't use linearity to pull this function here out of it.
Can you comment about the pi log x at the end? Why didn't the identity find it?
It's because the identity is essentially blind to pi, but there's some more general way to also take at least some of the pi's into account. So we can take via some more general Hopf algebra structure all of the pi's into account, except for in the last slot. But if we have everything taken into account for except in the last slot, then we can just evaluate it at some particular number and recover all the pi's. So there's a particular sense in which the symbol tells us something about the most complicated part of this identity, or the most complicated part of the result. And then there's a systematic way in which we can recover the simpler part that we are missing at the first go. I guess you would agree that this diagram here, it's more complicated than pi times the logarithm. And similarly, if you then go to the last step, you would say that I pi times the logarithm is more complicated as than the pi squared, right?
Right. I understood that. First, I understood that it's invisible to constants, but we are saying now that it's invisible to pi.
Yeah, it's the kind of constants we get here are pi, but then there's also stuff like multiple zeta values or single zeta values coming out of this. Because if you say evaluate this at x equals 1, you get exactly zeta of 2. And similarly, if you have a lie n of x, you get zeta of n if you set x to 1. So far, so good. Shall I continue, or are there further questions on the symbol for polylogs?
I guess you can continue.
Yeah. Okay. So the first time this symbol was really introduced to physics was in this dramatic simplification now 13 years ago of the two-loop 6-gluon remainder function in the maximally supersymmetric gauge theory, where it was possible to, using now more complicated identities at the symbol level, satisfy some result of 18 pages to just 2 lines. And moreover, it's also possible to use this symbol for a bootstrap. I was told that many of you are familiar with the conformal bootstrap. Here it's a different kind of bootstrap. And the way this bootstrap works is that we can just make an ansatz now for the result in terms of polylogarithms, because if we understand all of the identities, we can write down a basis of these functions. And then we fix the coefficients in this ansatz via physical constraints. And that way we can get the result without having to do any Feynman diagrams or Feynman integrals at all. And the first application of this was the 6-gluon remainder function, which after the initial simplification of the two-loop result was then calculated at higher loop orders up to 7 loop orders. And moreover, a similar story goes for the 7-gluon remainder function. But it's also possible to bootstrap solutions to differential equations. And something we've recently done is bootstrapping the n equals 4 equivalent, so maximally supersymmetric Yang-Mills theory equivalent of the Higgs to 3-gluon amplitude in the large top mass approximation. And this is indeed believed to give the maximally transcendental part also of the quantity that you encounter in usual planar Yang-Mills theory, so for actual Higgs physics at the LHC. And here I mean that we're getting the pieces with the maximal transcendental degree. So the pieces where we have the log of n, but not the pieces with a log of n-1. I mean, classical polylog n-1 is then something beyond what agrees between the maximally supersymmetric and the non-supersymmetric theory. So in this case, this simple alphabet, the letters here are log of these three here and also 1 minus them. So now S12 is just the Mandelstam variable defined via the square of the sum of these two momenta. And in total, if you define the U, V, and W like this, they sum up to 1 via momentum conservation. So it's a 2-scale problem, where indeed we could go to bootstrap this to 8 loop orders, something that's surely not possible with any other method as a closed form result for any value of 2 different parameters. And moreover, we encountered a new and surprising duality in this, finding that this Higgs to 3 gluon remainder function, I should probably have said before, is the finite part of the amplitude in a specifically defined sense, that this is really dual to the 6 gluon remainder function.
So you stop at the 8 loops because the space of functions is too large and you don't have enough coefficient, enough constraints to fix your answers, or
So
too hard to generate the answers.
So at general L loops, you have 2 L entries in the tensor product. So if here now you have an alphabet of 6 letters, and you're building something then at weight 16, you have 6 to the 16 different elements in your basis. And that's a fairly big number. You can do a bit better, but roughly when you have several millions of unknowns to solve for in your ansatz, then you're reaching the limit of computer clusters using finite fields technologies. So if you give us twice as big as a cluster, I mean 10 times as big as a cluster, I think a 9 loop would be easy. We're currently working on 9 loops, so there's nothing nothing conceptual stopping us. But at some point, we also want to just think about what's the structure, and maybe we can write down the all loop result.
Okay, so the main constraint is just the resources. It's not nothing fundamental.
Absolutely nothing fundamental.
Okay.
It's just that at some point you run out of steam, and you have to think again about how you are finding more structure in this result that you can observe at one loop order and then assume at the next loop order to find your answer being then smaller, your ansatz then being smaller, so you start with less coefficients, so you can actually do it.
Okay, thanks.
Thank you. So unfortunately, or maybe fortunately, no quantum field theory that we know stops really at these multiple polylogarithms. We also have more complicated functions, and in particular, elliptic integrals and their generalizations, as well as integrals over higher dimensional Calabi-Yau manifolds. So the prime example of this is maybe the banana graph, which at L loops and all internal masses being non-vanishing contains some L-1 fold. And you don't even need masses. This is a pure number in phi to the 4th theory, which is a period of a K3 surface. Even in planar n equals 4 super Young-Mills theory, we have these Calabi-Yau L-1 folds at L-loop orders. And if you're willing to go non-planar, we even encounter twice the dimension per loop order. So, of course, we'd like to have a similar understanding of these functions, find similar structures, and use similar techniques to go to very high loop orders. But let me maybe first answer the natural question of how do we even encounter something that's layering beyond multiple polylogarithms. So let's start with a, say, Feynman parameterization, where now these xi should be Feynman parameters. And now let's assume that our integrand is quadratic in the last parameter here in the numerator. And now this p is a function of the other Feynman parameters, but could also involve the masses and the momenta of the particles, as you're familiar with from the Feynman parameterization. But a similar story works also in Schwinger parameterization or everything else you could start with. And now to do the integral, we would partial fraction this here in xn. So you would arrive at some square root of this polynomial. And then you can do the integral in xn because xn just now occurs in this linear factor in the denominator. And what you arrive is essentially by the definition of what a logarithm is, a logarithm. But now you also got the square root involving all of your other parameters. And let's say we actually have only one more parameter to deal with. If the degree of this polynomial is now 2 or smaller, we can simply put a change of variables to rationalize the square root, and then we can go on in multiple polylogarithms. However, if the degree is 3 or higher, and no of these roots of the polynomial coincide, then it cannot be rationalized, and we cannot continue in multiple polylogarithms. And similarly, also if there's more variables left, and we cannot rationalize for any choice of the next integration variable, then we are leaving the space of multiple polylogarithms. So far, so good? Great. Now let's come to geometry. We can easily find geometry if you just give this square root a name. Let's call it y. And everything is just looking simpler in terms of y. But importantly, y is defined via y squared equals this polynomial. And if it's a polynomial of only one variable, this is an algebraic curve. And in particular, if the degree is 3 or 4 with no coinciding roots, it's an elliptic curve or a torus. Did somebody have a question?
No.
Okay, and if we have more generally n variables, then this defines here an n-1 dimensional variety. And this is similar constraint on the degree. If it satisfies, it tells us that this is actually a Calabi-Yau manifold defined by this equation here. And it can be singular. And of course, this is a special case of a Calabi-Yau, and torus is just a Calabi-Yau one-fold. Okay, so then let's talk a bit more about elliptic generalizations of polylogarithms. So what we have here is the elliptic curve in this Weierstrass form. And on it, we can define via iterated integrals also elliptic generalizations of polylogs. And here now, in addition to these integration kernels, which we had for the Gonchov polylogarithms, we could also build something like 1 over y, which is 1 over the square root of the polynomial defining the elliptic curve, or some suitably normalized product of the two, or some more. However, when we wanted to define a symbol, we required that the total derivative of this function gives us something simpler, and that's not satisfied for these. However, we can go to the torus from our elliptic curve using Abel's map here, which is just the integral of minus infinity to some point c of dx divided by y. That's bringing us that way. And to go back, we can use Weierstrass p function. And now on this torus here, we can define some functions gamma tilde, and we want this to be normalized. So we have these two periods here, but we actually want to rescale the torus so that this one is 1 and this one is omega 2 divided by omega 1, which we then call the modular parameter tau. And then we can do a similar thing to what we did for Gonchov polylogarithms. We simply define the symbol of these functions via the total derivative, which is again some forms multiplied with lower weight functions, simpler functions, and we define the symbol via this tensor product. And now, of course, these are more complicated than logs, but I'll show you in an example what they look like. One obvious question is then, how do we manipulate these? What's the analog of the identity here? Log of a plus log of b equals log ab. And that's something that can be solved using Abel's theorem and some elliptic Bloch-Wigner relations that can be manifested in a certain way that is a bit technical, so you can ask me later if you're interested in it. So now let's look at a simple example, the 10-point elliptic double box. So I'm thinking about this here in a scattering amplitude picture. So I would have the black lines be particles interacting in planar n equals 4 Super-Yang-Mills theory, where this is in fact the only contribution to a particular planar 10-point component amplitude. And it's in fact the first elliptic contribution that contributes to n equals 4 Super-Yang-Mills theory, if you like that theory. But you could also just look at the dual graph here and have a diagram contributing to correlation functions in phi to the 4 theory or fishnet's theories, or also n equals 4 if you want. So this depends now on 7 independent dual conformal cross ratios defined like this. And importantly, it also satisfies some differential equation, where if you're taking the derivative with respect to one of these cross ratios, we obtain the hexagon, but now in 6 dimensions. And as a prefactor, 1 over the normalized 6-point Gram determinant. Importantly, this here is a cubic polynomial in this integration variable. So this variable with respect to which we take the derivative. So if you try to integrate up this differential equation with respect to this variable, we arrive at something which contains an elliptic curve, so some elliptic polylogs. And you can actually do this integral with some hard work. and compute its symbol. And here we have a factor just for normalization to normalize by the leading singularity to make it pure. And then the symbol is essentially having a same structure for most of the entries, again, as for polylogarithms. So we have logarithms in the first and second entry, and in most of the third entries, and then the last entry is simple elliptic integral. So this is essentially what I had before as Abel's map. So that's what I would call a simple part. But then there's also the part here where the last entry is tau, the modular parameter. Then the third entry in front of it is more complicated, but can actually be fully obtained from the other entries here. So you say, see, it can be written as some derivative of an integral of now these here in the opposite order. So if we use this here to write everything in terms of the logs and these elliptic integrals, we find an alphabet, a set of building blocks, which just contains 53 of these logarithms, and then 6 of these elliptic integrals and 2 pi I tau. But as I mentioned, this was a lot of hard work. So as a next step, we want to actually exploit the structure and bootstrap something new. This 12-point generalization, where here I have now 2 massless legs. So these 2 points here are no longer light-like separated. And you might be interested in this one, I guess, from some correlation functions in fishnets or n equals for Super-Yang-Mills theory.
So how do you the arguments of the symbol? So
how we get them?
can you go one slide before?
Yeah.
So how can you get these pi i's if given the integral of your opinion?
So if I have done the hard work of calculating the result using some Feynman parameterization and writing in terms of these gamma tilde functions, I can use the definition of the symbol and then use these identities here, the analog of log of AB, to reduce everything to a suitably chosen basis. But that is the hard way. In the rest of the talk, I will tell you more elegant way how we can actually now guess the entries in this 12-point case without ever having to do the Feynman parameterization. Does that answer the question?
Yeah. Okay, but for this, it's crucial for the answer. So you write the Feynman parameterization in terms of okay, you write the Feynman parameterization, right?
This is what we did in the 10-point case, yes.
Okay.
So there we just did the integral, computed its symbol, and after some simplifications found this result. But what I'm going to argue in the rest of the talk is how to do it more cleverly and circumvent the whole calculation.
Okay. Then I guess I can focus on this more clever way.
Great. So what we're now looking at is this integral, and actually with our means at least, we cannot calculate it with the Feynman parameterization. So we had to come up with something more clever. And it's a function of 9 independent cross ratios, satisfies a similar differential equation. And because we can't get it from Feynman parameterization, at least we couldn't, we developed a bootstrap for it. And for this bootstrap, the first step is to generate the letters. so generate the building blocks, answering the question via geometry that was just asked, and then gluing these letters together to build functions from them, and finally some results. So let's look first to see how it works at a very simple example. So this is now the box in 4 dimensions, a one loop integral. And if you do this integral, you find that maybe your dual conformal cross ratios u and v are not the most suitable variables, but rather you want to define some z and z bar, which are defined in terms of u and v in this way. So in particular, we have the square root in the problem, which becomes rationalized if we use these clever choice of variables. And again, if you do the calculation and you calculate the integral, from it calculate the symbol, where here now we normalize it by the square root to make the function pure, so that it becomes simpler if we take derivatives. We find this simple expression. And the first letters here, u and v, can also be written as z bar, or 1 minus z bar. And then the second letters here are these ratios. And now the question is, how could we arrive at these letters here without doing the integral, as a warm-up of doing the same for the double box? And here actually some beautiful geometric picture comes in. And to see this picture, we can use momentum twistors. So who is familiar with momentum twistors?
Probably no one.
Okay. So it's a beautiful story, with, of course, starting with Penrose, but later picked up by Hodge, that for every dual momentum point x here, we can associate a line in projective space. So here we have this number, which is a 2-component object. So in total, this has 4 components, but it's in projective space. So we can always set the first of these 4 entries to 1 if we want. And then the second one means that we have 1 parameter parameterizing this line. And now we can also rewrite the integral using these so-called Plöcker coordinates in terms of an integral over twistors, where now we have these 4 brackets, which are essentially determinants. And now, yeah? Any questions about twistors?
Yeah, not about this part, at least.
Okay. So if we now go to twistor space and we want to consider the leading singularity of this, so we want to deform our integration contour such that it encircles this pole here. That means we want to impose these so-called cut conditions in the amplitudes literature, where this is 0. And in twistor space, now, or rather in dual momentum space, this means that this dual momentum and the integration point here are light-like separated. But in twistor space, this means that the lines corresponding to this dual point xi here and the line corresponding to the integration point, they intersect. And then imposing the next cut condition, also the next lines have to intersect, and so on for the third and the fourth. So to sum this up, the maximal cut condition, which gives us the leading singularity, can be found by solving a line in twistor space that intersects all the external lines. And this problem of finding lines that intersects other lines is actually one dating back to the 19th century, known as a Schutbert problem. And this was recently applied to predicting these symbol letters. So in particular, in twistor space, we can parameterize the twistors corresponding to this integration point in a particular fashion, and then imposing the cut conditions. We see that this first one here drops out, imposing the second cut condition, next thing drops out, and the last two cut conditions then give a quadratic equation for alpha and beta. So we actually have two solutions to this, since it's a quadratic equation. So now, of course, here we have 4 points on the line. And if you have 4 points on the line, we can define two multiplicatively independent cross ratios. So let's just call them U and V here. And you can calculate that in this example of the 4-mass box. These really are evaluating to Z, Z bar, 1 minus Z, and 1 minus Z bar. So by taking their products or quotients, we can obtain the rational and algebraic symbol letters we had in this symbol of the 4-mass box I've shown you a couple of slides ago. Any questions on this geometric story?
Sorry, why do you need products and quotients?
So what we found in the symbol, just experimentally, if you want, is that the symbol here was containing the U and the V, which could be written as Z, Z bar, or 1 minus Z, 1 minus Z bar, or the respective ratios. So just experimentally, we found that those are the symbol letters. And now, if we go through this geometric construction and we look at our cross ratios, we find that the cross ratios themselves are just Z, Z bar, 1 minus Z, and 1 minus Z bar. So to actually get the symbol letters, we then need to take products and ratios.
Okay, but let's suppose that it's not a log. Like in this case, like this, of course, you get these cross ratios, and then you want to find the same symbols as before. So you see that you take products or quotients, and as these are only logs, actually, that's the only thing you would like to consider, I guess.
Yeah.
But if it's not a log, or if you don't have a way to compute this integral in a given form, how do you guess that it's like this is a prescription that seems to work, or?
It's a prescription that seems to work. And the beauty of the bootstrap is that we need an ansatz. We need to just have a guess, and then we can check it. We can impose constraints. Maybe we don't find a solution, and then we need to make our ansatz bigger and get better at guessing. Or we find that our ansatz was actually overdoing it, that we could have gotten away with a smaller ansatz, and then in the next case, we use this knowledge and start with a smaller ansatz.
Okay, thanks.
Okay, so let's go to the 10-point double box. Here again, we start with the logarithms of now the 9 independent dual conformal cross ratios. And this also follows from the first entry condition, as it's called. So I told you before briefly that the first entry is telling you about the discontinuity of this function. And we know that, say, in QED, the threshold for particle production is 4 times the electron mass spread, but here we have a massless theory. So the threshold for particle production is where some Mandelstam is 0. And U was a cross ratio, so it was a ratio of products of Mandelstams. So this logarithm here has the branch cut starting in exactly the right place for the threshold for particle production. And now then we can go through the second entries. And now we have, of course, these 6 points, dual points in the double box, but then we can choose 4 of them to get a 4-mass box. So from this subtopology, we get then another 15 times 2 for Z and Z bar equals 30 ratios and products. But of the products, actually only these 9 are linearly independent. And then we can see that actually we're on the right track. This reproduces what we have for the 10-point double box. And now for the third entry, we have to do more things. We have to overlap, say, 2 of these sub boxes that we have in the double box. And now we can look at here this line and form some dual conformal, some cross ratios. But actually what we need to do is intersect 4 of these boxes. And then there's a number of choices. And for each of these lines with 6 points on it, we have 9 independent cross ratios. And we get 134 letters. And now if we look at the leading singularity, I promised that there would be something elliptic. So here in the dual graph, if these red lines are light-like separated, we have in 4 dimensions 8 variables for the integration, but we impose now 7 constraints. So there's a 1-parameter solution to this Schubert problem here in twistor space, and this is in fact giving some elliptic curve. And now here, of course, we have no logarithm anymore, but the natural form in this elliptic curve is just dx divided by y. And this elliptic curve intersects, say, if this black point here is on one of these lines, it is the solution to the previous Schubert problems. So there's also natural integration boundaries. And if we do this, we find 9 independent last entries. So far, so good. Is that in particular giving also the required details for the calculation that you asked about beyond logarithms?
Mm-hmm.
Okay, then we can now put everything together. And here the question is actually any tensor product I can write down something legal? And the answer is no, because I know that the symbol is defined via the total derivative, and total derivatives commute, but this isn't necessarily the case for any tensor product I'm writing down. So let's say I start with a candidate log U tensor log V. If I now take the commutator of the derivatives acting on this one, this here gives 1 over U, this gives 1 over V, but in the other direction it gives 0. So the commutator isn't 0. Instead, we can symmetrize it here, and then we obtain something that's legal. So this is imposing constraints for us. And now we can use the constraints here to bootstrap it. So we start with this alphabet with 9 times 39 times 134 times 8 letters. 8 letters mean, because we are not putting the tau in, because the words ending in tau are determined by all others. And then imposing integrability in the first 2 slots, we get down to 60 from this slightly shy of 400. In the second slot, we get some 19. And then if you combine them, we only got a single overall free parameter. So just imposing that this is actually the symbol of a function fixes the solution to a unique answer up to an overall scale. And then we can use the differential equation to fix this normalization constant, which also gives a lot more constraints. And we can also check with the permutation symmetry, with the 10-point limit and some further relations that we actually got the right answer. And here, and we never had to do more than solving a system of 1,000 unknowns at a time. So much better than the 8-loop calculation where we had to do millions of coefficients. And if you look at the results, it's best to recall this differential equation and that the symbol of this hexagon was actually given by some kind of boxes and some logarithms involving here these ground determinants. And then the symbol has a structure which is fairly suggestive of just integrating up this differential equation. And if you want everything fully explicit, I won't go introduce the notation, but you can even fit it on one slide if you spend a bit more time on explaining the notations. But it's a fairly nice structure, fairly short result. So let me now come to a conclusion. I've shown you how Feynman integrals show a rich number theoretic structure, ranging from polylogarithmic functions to elliptic ones to integrals over Calabi-Yau manifolds. The bootstrap is something that works amazingly well up to 8-loop orders for this polylogarithmic case. But what I've shown you in particular here is that also in the elliptic case, we can actually use it as an alternative to integration, circumventing all the problems that integration has. And in particular, I showed you some geometries, some Schubert problem to actually guess the letters. And then, of course, there's many more things to be done. In particular, it would be also interesting to generalize this to the whole Calabi-Yau integrals. But now I think I'm out of time. So thanks a lot for your attention.
Okay, guys, let's thank Matthias. Very nice. Any questions? Yeah.
So the generalization of this determinant that you have, for example, for the 6-point one looping in 6 dimension to the
So, you mean here this
okay,
part,
so
right?
they're a delta 6, right? That's the leading singularity, right? Of that integral, delta 6.
Yes, this is just the leading singularity of this integral, yes.
Okay,
So this is supposed to be understood as the version that is divided already. I mean, where I factored out the leading singularity, right?
yeah, so the leading singularity for this 12-point integral is just this omega 1 in a
The leading singularity of the 12-point integral is essentially this one.
Okay.
So, I mean, it's the leading singularity is imposing, of course, 7 conditions now only on 8 integration variables. So you have one final integration left to do, and you can choose naturally the A cycle or the B cycle of the elliptic curve, and then you get either one period or the other.
Okay. Okay, so that's the reason why you don't get a simple function as determinant of something, right?
Yeah, I mean, you need to have something which is an integral over something, because the leading singularity does not fix all of the integration variables to be localized at a pole, because there's just not that many poles. We can't take that many residues. So we have to integrate.
Okay.
Other questions?
Does this analysis also work for equals with numerators? I think the amplitude also has those, right?
You're asking about numerators.
Yeah.
So in principle, I would expect it to work also in this case. I mean, here, of course, this is the first example anyone has ever done for bootstrapping an elliptic Feynman integral. So all of our intuition, apart from that one case, has to come from the polylogarithmic versions. But there in the polylogarithmic versions, you see that, I mean, at least if you're bootstrapping some scattering amplitudes, there's the sum over all Feynman integrals. But I guess in the special case, if you have one in mind, we need to look at it and think about if the alphabet is growing because of the numerator or not. I wouldn't expect it, but this is really interpolating from one data point, so don't take my word for it.
Does the result simplify if you consider specific kinematic limits, like you have when you consider all points to lie on a plane, for example?
If you take all points to what?
To lie on a common plane.
Yes. Then it simplifies dramatically. So I mean, there's good limits you can take and not so good limits you can take. For example, one good limit you can take is to the 10-point double box, where you take this one to be massless. But say if you take this one to be massless, to have these two dual points like separated, then you develop some IR divergence. And then, okay, the simplest way I know how to deal with it, just take the whole result and use this dual conformal regulator of Simon-Caron-Yau, and then you can regulate this divergence, which boils down to computing this original diagram. But okay, if everything is on the same line, that looks highly singular to me, because then all of these determinants here seem to vanish, right?
Yes. So on a line, yes, but on the plane, does it also vanish?
I mean, I think on the line, all of the determinants vanish, but this doesn't mean that the result vanishes. It just means that you have to be more careful in calculating these limits. I mean, also, there's cases, well-known cases in the polylog world where you have weight drops because the integral divided by the leading singularity has the property that the symbol letters diverge, but then this leading singularity diverges also. So if you take the right combination, then you do some more fancy version of de L'Hopital's rule to actually calculate that limit, and you get some weight drops in the polylog world. So I would expect something similar here. But of course, it's if you're interested in some configuration where all of the deltas here simplify, it might be easier to just start with that configuration and not take it as a limit of something much more complicated.
Yes.
So, for example, if you take this one here, soft, that's something you can do on the bootstrap side, on the symbol side. It's reasonably complicated because you have to pick the right normalization. In one of the normalizations, this period here blows up, but the other one doesn't blow up, and then you have to find the right contour also here, or combinations of contours that are not pinched by the roots in this limit where the elliptic curve degenerates. And you can do the analysis we did in this paper from last June, but it's actually way too complicated. You can just start with the Feynman parameterization at the level of the Feynman parameterization, take this here to be soft, and then you put it into hyperint, and hyperint gives you the result without any spat.
Yeah, I guess you're talking about putting it soft, but I was more interested in setting all points to be on a common plane. But I see. But you didn't try to reduce the number of. Here you have some 9 cross ratios, right? In the full.
Yeah, we have 9 cross ratios. Yes.
Yeah. So in this configuration that I was mentioning, you reduce the 9 to just 6. I know that this hexagon integral simplifies a lot in that limit. I was wondering if the 12-point integral also simplifies.
Yeah, I mean, this will dramatically simplify in the limit. I just haven't worked out the details.
Okay.
But I mean, if I were to work out the details, I would proceed along the same lines of what we already did now last June in this paper with Zhezhang and myself for the example of the 10-point case. And then it should work pretty straightforwardly as a generalization of the 10-point case, taking this limit.
Okay, thanks.
Other questions, comments? Okay, if not, let's thank Matthias once again.
Thanks a lot for the invitation.
Thank you very much, Matthias.